In the world of machine learning, it's kind of funny. Sometimes the simplest algorithms are the most powerful, but even the best tools can have a hidden flaw. Today, we're going to dive into a classic, the naive Bayes classifier. We'll look at its one big weakness and then a really clever fix that makes it way better than you'd think. But first, to get our brains warmed up, let's try a little puzzle. Imagine a couple has two kids. All we know is that at least one of them is a boy. So, what's the probability that they have two boys? Now, your gut reaction is probably 50%, right? One's a boy, so the other is either a boy or girl. Simple. But like a lot of things in probability, the first answer that pops into your head isn't always the right one. The actual answer is 1/3. Yeah, I know, it feels weird. But here's why it works. If you think about all the possible combinations for two kids, you've got girl-girl, girl-boy, boy-girl, and boy-boy. The puzzle tells us at least one is a boy, so we can just throw out the girl-girl option. That leaves us with three possibilities, and they're all equally likely. And out of those three, only one of them is boy-boy. So, 1 out of 3. This little puzzle is the perfect key to unlocking the really powerful idea at the heart of our story today. And that big idea is called Bayes' theorem. Really, all it is a formal way to update what you believe when you get new information. It's the math that solved our puzzle, and more importantly for us, it's the engine behind a really popular machine learning algorithm. So let's finally meet this algorithm. It's called the naive Bayes classifier. And that word naive, well, that's exactly what we're here to talk about. Despite having naive in its name, this thing is an absolute workhorse in machine learning. It's famous for being incredibly fast, super simple to implement, and shockingly good at classification, which is just a fancy term for sorting things into different buckets. And I guarantee you've run into it out in the real world. It's the kind of thing that powers the spam filter in your email, helps classify news articles, drives recommendation engines, and is even used for things like medical diagnosis or predicting landslides. It's simple for sure, but it gets a ton of work done. But here's the catch. There's a reason this algorithm is so fast and simple. It's because it makes one huge and, let's be honest, usually wrong assumption about how the world works. This is where the naivete comes in. The algorithm assumes that every single piece of evidence, or every feature in machine learning terms, is completely independent of all the others. It's called the conditional independence assumption. So, what does that actually mean? Let's go back to that spam filter. The naive assumption means the algorithm sees the word free and the word money in an email and treats them as two totally separate, unrelated clues. But you and I both know that's just not how it works, right? In a real spam email, if you see the word free, there's a pretty good chance you're going to see the word money too. They are not independent. And this, right here, is the algorithm's Achilles heel. Because the real world is messy and everything is connected, this flawed assumption can create bias. It can cause the model to make mistakes, and even worse, be way too confident when it's wrong. For the longest time, this was just the deal. You wanted the speed and simplicity of naive Bayes, you had to live with its big flaw. But what if you didn't have to make that trade-off? What if there was a way to fix it? The core idea is actually pretty brilliant and simple. What if we could just teach the algorithm how much to trust each piece of evidence? What if we could tell it, hey, listen, these two clues are basically saying the same thing, so don't count them both at full strength. This is the whole concept behind attribute weighting. So here's how you can think about it. Standard naive Bayes is like a jury, where every juror's opinion is counted equally. But a weighted approach is more like having a jury foreman who can say, okay, everyone's input is valued, but this juror over here is an expert witness, so their opinion gets a little more, well, weight. The algorithm actually learns the perfect weight for each feature, which lets it tone down the impact of those features that are messing things up. So a group of researchers developed a method to do this, and they gave it this amazing nerdy name, WANBIA. It's an acronym that stands for Weighting Attributes to Alleviate Naive Bayes Independence Assumption. It's basically a smarter, upgraded version of naive Bayes that learns how to correct its own flawed view of the world. Okay, so the theory sounds great. It's an elegant solution, but does it actually work when the rubber meets the road? Let's take a look at the data from the paper that introduced this whole idea. The researchers basically set up a head-to-head competition between WANBIA and regular naive Bayes, testing them on 73 different real-world datasets. And the results? They weren't even close. When it came to bias, 1BA won 57 times. For just plain old error rate, it won 49 times. The numbers don't lie. The fix absolutely works. But getting more answers right is only part of the story. The fix also improves something called probability calibration. And in simple terms, that just means the model's confidence scores become a lot more trustworthy. So what is calibration? Well, think about a weather forecast. If it says there's a 70% chance of rain, you'd hope that, over time, on days with that forecast, it really does rain about 70% of the time. That's good calibration. Standard naive Bayes is like that forecaster who is always yelling, 100% chance of a hurricane. It's just way too overconfident. When Bayes' weighting system dials back that overconfidence, making its probabilities a much better reflection of reality. This graph from the paper is a great picture of how this correction actually works. Don't worry about the numbers on the axes or anything. Just look at the lines. That solid red line, think of that as the initial overconfident guess from the original naive model. And that blue line represents the correction factor. That's the fix that the weighting system learns to apply. And when you apply that blue correction to the red guess, you get the final dotted black line, which is a much more accurate, much more realistic prediction. This is literally a picture of the model learning to correct its own mistakes, which is exactly what Wanbia was built to do. Okay, so we've got a simple, fast algorithm with a known problem, and we've got a really smart fix that makes it way better. So what does all this mean for the big picture of machine learning? Well, what happens when you take this souped-up naive Bayes and put it up against the modern complex giants, like random forests? Something really interesting happens. On small to medium-sized datasets, which, by the way, is a lot of real-world problems, this improved simple model is incredibly competitive. Sure, the complex models might pull ahead on gigantic datasets, but they do it at a massive cost in computing power and time. And that gets us to a really powerful point. Sometimes an elegant fix to a simple model is way more practical and efficient than some complex, gas-guzzling behemoth. It's a fantastic reminder that in this field, smarter does not always mean more complicated. And maybe that's the real lesson here. Innovation isn't always about inventing something totally new from scratch. A lot of the time, the biggest breakthroughs come from looking at the great ideas we already have and just figuring out how to fix their bugs.